Hi everybody, I'm Jiran, and I will introduce our work EZCrop Energy Zoned Channels for Robust Output Pruning. The source code is available on GitHub as shown in the lower right corner. My talk will be in 4 parts, including the preliminary, our proposed EZCrop, experiments results, and towards the end, a conclusion of this work. Let's go over the convolution in the spatial domain first. We know the filter slides along the H and W axis of the input and does the standard convolution with the input in the kernel window. Next, let's see the convolution in the frequency domain. First, each slice of the input and filter will be mapped into the frequency domain by the 2D fast Fourier transformation. Next, the slices at the same position along the channel axis will do pointwise multiplication. After this, all the pointwise multiplication results will be added together. By the multiplication and addition, we get the convolution results in the frequency domain. In our work, we find out there is a connection between the rank in the spatial domain and the low frequency distribution in the frequency domain. In other words, it is promising that we can use the low frequency distribution to evaluate the importance of filters. Based on the observation, we proposed EZCrop to quantitatively describe the degree of dispersion of low-frequency components and use it as a metric in the frequency domain to evaluate the filter importance. There are 4 steps in EZCrop. The first step is to find the square center, namely the DC component center. For width and height, we consider 2 cases, even and odd. The second step is to decide the expanding distance, which decides the size of the matrix, taking the DC component as the center. LIH and LIW are the distances between the center and the last row and last column respectively. Then if one of them is smaller or equal to 1, the expanding distance will be set to 0. Otherwise, we need to set a hyperparameter beta to decide the expanding distance. The right part figure shows the examples when DI equals to 0, 1, and 2. In step 3, we sum up the energy in the selected energy zone and the whole feature map. Then we calculate the average of the ratios and subtract it from 1. If eta is large, it means the low frequency components are dispersed, and the filter will be reserved during pruning. The final step is to sort the filter according to the metric. For example, filters with larger eta are more important. Firstly, we compare the time to generate the filter evaluation metric. Apparently, the time required by EZCrop is much shorter in all models. Noticeably, the larger the dataset, the more pronounced the efficiency of EZCrop is. For Silverton dataset, we take a look at the results of VGG16. It is obvious that EZCrop always gets better performance when compression level is similar. It beats HRank and other sorter pruning approaches. For more complex dataset ImageNet, we show the results of ResNet 50. The results equal to VGG16 on Silverton. Now let's look at the repetitive pruning results of ResNet 56 on Silverton. The results are reported in the table. We can see in each pruning process, EZCrop has higher accuracy. Besides, the accuracy gap is enlarged after each single pass. This obviously shows the EZCrop enjoys higher robustness under repetitive pruning, and it is able to evaluate the filters more accurately in each single pass. To show the robustness, we also compute the standard deviation by repeating the selected experiments for 20 times. This again verifies that EZCrop makes more accurate and robust evaluation of filter importance. In conclusion, this work connected the matrix rank in the spatial domain to the low frequency component distribution in the frequency domain. Second, according to our time comparison experimental results, the proposed F50-based metric for filter importance evaluation is efficient. Third, EZCrop brings higher resolution in channels importance evaluation compared with the rank-based metric. Fourth, EZCrop constitutes a robust way for repetitive channel pruning, which is verified by the repetitive pruning experiments and the STD analysis. That's all of our representation. Thank you for your attention, and if you have any question, please contact us.